All right, so we are ready for our next chapter, chapter 4. This one deals with energy and the society. So it turns out that sometimes we're not necessarily concerned about what products actually occur. So let's say you're going to react a hydrocarbon and oxygen. And it turns out if you take a hydrocarbon and oxygen and you react them together, you would end up with carbon dioxide and water. You're not concerned about the carbon dioxide and water in that case. You're concerned about the energy that's also produced. So that's what this chapter deals with, energy and how our society uses it and almost gets to the point of abusing it just a little bit, but we'll talk about it. Are there any long-term effects from that energy use? What concerns do we have about the environment and our climate? And yeah, just some different things about energy. Oh, and petroleum fuel. Whenever you go to the gas station and fill up, how is chemistry related to that? So I hope you learn a lot. So if we're going to talk about energy, well, we really need to define what energy is. Energy is defined as the capacity to do work. Okay, what's work? Work is the force acting through distance. Normally, when you talk about energy, and you talk about two different types, you talk about potential energy and kinetic energy. Potential energy is stored energy, or due to the composition of a compound is how we're actually going to talk about it. And kinetic energy is the energy of motion. And then we have this thing called the law of conservation of energy that states that energy cannot be created nor destroyed. Sometimes it goes on to say that it can be transferred from one type to another. So to kind of give us a demonstration, a visual of this, over on the side you have a person jumping off of a cliff. At the very, very top, they only have potential energy. That's energy due to position. You had to do so much work to climb to the top of that cliff, so that work has been changed to potential energy. And that's what you had, the stored energy. And as soon as you step off that cliff, that stored energy is transferred or transformed into kinetic energy. The total energy, it never changes, but we can change from kinetic to potential between those two parts. And as that person gets closer and closer to the water, they're going faster and faster. More and more of that potential energy is transferred to kinetic energy until right before they hit the surface, where we've transferred all that we can, and then it hits the surface and it dissipates and does all sorts of good stuff. Interesting stuff. Now, my son actually had an experience. Okay, he wasn't jumping off of a cliff. He was hanging on a monkey bars, and he fell off the monkey bars. He let go. And when he was sitting there, it was all potential energy, but when he let it go, that potential energy started transforming to kinetic energy. Unfortunately for my son, he fell face first on the ground, and he had wrapped his bottom lip around his tooth, and it fell right through. That was bad. It was really, really bad. So he had like a flap on the inside of his mouth. Oh, it was so gross. We took him to the emergency room, and just in case you were curious, since it didn't actually break the skin, you could see the indentation of his teeth, but because it didn't actually break all the way through, they didn't want to put stitches on the inside of his mouth, so they just let him go. So 4 hours in the emergency room, only to have nothing done. So hopefully you don't have that particular experience, but jumping off a cliff like that, that's kind of cool. Recently we went to a place called Blue Hole in New Mexico. It's an 80-foot swimming hole, if that's how deep it is. And so there were little cliffs that my husband and the kids jumped off of. Pretty cool stuff. Now, when you go to big boy school and you do anything in engineering or physics, you can take entire semesters based only on this subject of thermodynamics. So what we're trying to look at here is the relationship between heat. Heat is a transfer of energy from hot to cold, and some other type of energy. So what's the relationship between the two? Now with thermodynamics, there's 4 laws that people will normally talk about, but we're only going to discuss the 2. The first law of thermodynamics states is the conservation of energy. And we just learned about that on the previous slide, where energy cannot be created nor destroyed, but it can transform from one type to another. So let's say you have a battery, and that battery has chemical energy. And we can take that chemical energy and we can transform it to electrical energy to be able to use whatever device you want. That's the first law. Total energy conserved. You can transform one type to another. The second law, let's read it here. Dispersal of energy associated with entropy. And entropy is a measure of disorder. Now, I know that doesn't make a whole lot of sense right now, but the idea is that the universe is becoming more and more disordered, and the way things like to go is more and more disordered. I mean, think of your room. If you don't do a lot of work to keep it clean, what happens to it? It gets more and more disordered. So that is what the second law is trying to talk about. So this could be applied to as you're doing a conversion from one type of energy to another, that some of that energy is lost to heat, that the conversion is not as efficient as we would hope it to be. So if you are running a motor, some of that energy is lost to heat. We got a brand new vacuum this weekend, and after we ran the vacuum, it was extremely hot. Well, that heat, it's not doing any useful work that you'd want to see, but we're losing some of that energy due to this heat. It's not the most efficient thing in the world. That is the second law. The second law also applies to things becoming more and more disordered. So down on the bottom, it has a picture. If you take a glass and you add just a drop of dye, if you haven't ever done this, go do this at home. It's kind of fun. And you watch it, that dye starts to spread out. It doesn't stay in one place, it starts to spread out. And as it spreads out, that system, so what you're looking at there, that system becomes more and more disordered. That is the second law. So we talked about the two laws, so let's do an example. And you're going to tell me, is it the first or second law of thermodynamics? The first example that I have says the energy supplied by foods is conserved, though it may be converted into work and heat. What do you think, first or second? That would be first law. We have the idea that energy is conserved, and we're transforming it into work and heat. Whether or not that's efficient, that's second law. But first law just says total energy is conserved. Well, let's look at the second example that we have. We cannot fully utilize the energy of foods, since some of this energy dissipates from the body as heat. Well, I kind of gave it away. Sorry. That one is the second law, where we're saying it's not necessarily the most efficient thing in the world, where we're going to lose some of that conversion, some of the energy due to that conversion as heat. And so it's kind of, I don't want to say lost, but we're going to say it's not being utilized. So as we start talking about energy, we need to talk about the units that energy is measured in. So we're going to talk about a couple of the more common ones. So a lot of times with energy, we hear about calories. Now you're going to hear a lot about calories in the next chapter, which deals with food. So calorie is actually a British unit. And the first thing I want you to notice, and it says it on there, notice that there's a little C at the beginning of that. Now that little C, I'll even highlight it right here. The C at the beginning of calorie right there. Now, that can sometimes, I don't know why they did this, but for whatever reason, they decided to get a little tricky. So calorie was originally defined as the amount of heat to raise 1 gram of water 1 degree C. Whew. Well, it's a really, really, really small unit. And so generally we use kilocalories. Now kilocalories, that prefix kilo, remember that means 1,000. A kilocalorie is 1,000 little calories. Well, then whoever it was came up with this great idea that they said, you know what, these kilocalories, those are going to be our dietary calories, and so we're just going to call it a calorie. So 1,000 calories is just going to be called a calorie. But what they did to tell a difference between that and the little calories is they put a capital C on it. I know, it doesn't make sense, does it? You're going to see that a lot more in the next chapter. Now, that is a British unit. Another British unit you might see is a BTU, a British thermal unit. So those are a couple that you might hear of. In this class for food, we'll talk about calories, but then when we talk about energy, we actually talk about joules. Joules is the SI unit, so it's actually based on the metric system. If you look at where it comes from, it is a kilogram meter per second squared. I know, another crazy unit. And they didn't want to say kilogram meter per second squared over and over, so they gave it a brand new name. They call it a joule. Now, joules were named after a guy named by the name of James Joule, who was a 19th century English physicist. Wow. Who did a lot of work in this particular area. Now, 1 joule is equal to 0.24 calories. So a calorie is bigger than a joule, and that's a little calorie. So a joule by itself still isn't very big at all. Now, where is energy being used? Well, down the bottom we have a pie chart. I would probably make sure to know the top 1 or 2 places, or 3 or 4. There's only 4 of them on this one, that energy is used. The top is industrial. So industrial includes all of your factories. So factories are included in industrial. Transportation, well, that's transportation. That is, how do you move products from one place to another? So all of your cars, all of your semis, and your plane fuel, anything like that, that's going to be involved in transportation. Residential is next. Residential is just what it sounds like. It's your homes. So how much energy do your homes take up? And then the final one is commercial. Now, commercial, sometimes they'll actually add municipal onto this one also. Commercial and, my pen's not writing. There it goes. Municipal. So this is hospitals, schools, street lights, traffic signals, that type of thing, where it's not necessarily one individual person, it's not necessarily industrial, but it is things that are going to be used kind of by everyone. So top one, industrial, and then transportation. Remember that. Now this is just kind of a random fact. I'm going to put my glasses on so I make sure I can read this one right. Currently, the U.S. consumes about 100 quads per year. And a quad, in this case, is a quadrillion BTUs, or a British thermal unit. Just to give you an idea of how big this is, a quadrillion, is 1 times 10 to the 18th joules. This is a huge, huge amount. There's about 5.5 million homes in the U.S. That are contributing to using that amount of energy per year. It's all the energy, but that kind of gives you an indication of the size of the U.S. here. And this would be equivalent to the energy produced by winds of a medium hurricane over several days. Now, comparing that to worldwide, we use 100 quads. Worldwide, there's about 500. So we use about 20% of the energy throughout the world. Now it's expected to grow to about 700 quads per year by 2030. So energy demand is definitely going up. So we got to put out a little question for you. This one says, what sector consumes the most energy in the USA? Transportation, residential, commercial, or industrial? Do you remember the pie chart? Yes, it is industrial for this particular one, and industrial was about 31%. Next one was transportation. All right, let's keep going. All right, now this question goes back to the beginning of the chapter, so let's see how good you do. If a spontaneous event occurs, the natural direction of change, then the entropy of the universe has decreased. True or false? Your answer should be false. So if a spontaneous event occurs, natural direction of change. That means that more and more things become disordered. We're going to have an increase in entropy. So your room getting messy, it's not necessarily your fault. At least that's the excuse I'm going to use.